Today we are going to start on designing a crest vertical curve. So the design criteria for vertical curve is basically the stopping side distance. That's the governing factor. The stopping side distance for the vehicles on the curve. So basically, our objective that a vehicle driving on this vertical curve is able to see another vehicle stopping or another obstacle on the other side of the curve. So this is basically the design criteria. So what is the height? Here, that's the height of the eye of the driver. So H1 is basically height of eye above roadway surface, and it's usually 1.05 meter. Okay. And here, the height of object above road surface. I believe it's 0.4 meters. I think it's 0.6. 0.6. Hold a second. 0.6. So this is 1.08 meters. Okay, let me just erase this. Here is the eye of the driver, and the height of the eye for the driver, above the roadway surface is 1.08 meters. The obstacle height, the driver should be able to see something at 0.6 meter height. Okay, so that's basically the design criteria. The L, so here we assume, first we assume that the stopping side distance S is less than L, and we substitute in this equation. Based on this calculation, if L is less than S, then okay, that's a correct design. If L ends up greater than S, then we move to this equation and calculate the length of the curve. Based on the length of the curve, we can decide, okay, the stations for the beginning and the end of this curve. Any questions so far? This is an abstract form based on height of eye of the driver and based on the height of the obstacle. So the first equation, it can be reduced to this form, and the second equation, it can be reduced to this form. So that's not the only design criteria. So we have what we are calculating here, we're calculating the length. Okay, for the design of sag vertical curves, the situation is different. We don't count only for the stopping side distance. No, the headlight here we're counting for the headlight stopping side distance. Okay, for the passenger comfort, for the drainage control, and for the general appearance of the curve. So for the vertical sag, okay, we have 4 design criteria that we must fulfill. So for the passenger comfort, for the stopping side distance, that's the starting point. We start with this, calculating the length of the curve. Okay, then we check for the passenger comfort, that L should be at least this value, where A is basically the algebraic difference in grades percent. That's A, the absolute difference between the two grades. L, minimum length 30A. Okay, and for drainage, the rate of curvature should be L over A, should be less than or equal 51. And for passenger comfort, this value, L should be greater than or equal this value. Okay, which is A multiply V square, the design speed in kilometers per hour, divided by this value. Okay. Okay. Here, these two equations are the same. If the stopping side distance was greater than L, then we turn to this equation. Okay, and this is the simplified version of that equation. So before we go ahead, we need to have an example. So we're going to take an example and we try to solve it. And so let's see what we got here. We have two segments. For the given segment of road vertical alignment waypoints data, road design data, 2 lanes, VD design speed is 90 kilometers per hour, level of service C, percentage of trucks 5%, draw and sketch a sketch for these stations. So we are going to draw first a sketch for these stations. So we have station 1, it's going to be station, okay, let me just zoom a little bit. So station 1, it's going to be at this point, and station 2 is going to be at this point, perhaps. I'm just plotting for the elevations. Here we have elevation 212.5, and here we have elevation plus 2 to 2.88. Then we have another elevation here, which is 242.88. So basically, that's what we got here. So we are planning to connect these stations with a vertical curve. These stations are not the point of vertical curvature at all, and this station is not the point of vertical tangent, but this station is the point of PI, point of VI, point of vertical intersection, and its station is basically 2 plus 8, 7, 0, 7, 2.0. The station 1 is 2 plus 5 to 6.0, and the station 3, which is this one, is basically 3 plus 1 to 2.00, and that's elevation. So before we start the design, we need to calculate the grades. So we have here G1 and here G2. So first of all, we need to calculate G1 equal delta Y over delta X. That means we subtract the elevations. We have 222.88 minus 212.5 divided by the distance. The distance is going to be 2 plus 872.0 minus 2 plus 526.0. So the elevation will be, we have 8 and here 3.01 divided by, we have here 6, 4, 3. So that will be 10.38 divided by 346. It's going to be 3%. Grade 2 equal delta Y over delta X, and this is gonna be 242.88 minus 222.88 divided by 3 plus 122 minus 2 plus 872 equals, here we have 20 divided by let me just do this quickly, 2872, 250. So that's basically 8%. So we have the first grade is 3% and the second grade is 8%. Next, we need to calculate the stopping side distance. Stopping side distance, S. So the stopping side distance in this case would be the design speed 90 over 3.6 multiply perception reaction time, in this case is going to be 2.5 plus 90 over 3.6 squared divided by 2 multiply G 9.81 multiply AY. Here F plus or minus G percent 0.01. Which grade of these we are going to calculate, take into consideration? Are we going to take positive or negative? Any suggestions?
Negative, Doctor.
Good. Which one? The highest or the lowest? We are going to take the worst case scenario. We are going to take as if the vehicle was approaching from this direction. That will give me the worst case scenario. Okay, so we design always for the first case scenario. Okay. So this will be 181, I'm sorry, 181.4 meters. Okay, now what type of curve we have here? We have a sag curve. So which formula or which equation we use for the design? Okay, we have a sag curve. So let's assume that let me just copy this with us. Let's say that we have that we have the L, the length of hold a second. Where did this go? Okay. Okay, let's assume that the stopping side distance is less than L. So we are going to use this equation. So we start here and say design. So we calculated the grades between the stations, estimate the equivalent grade for this segment, We'll talk about this later. Determine whether climbing lane is needed or not. Design the, we are working on the design. We will come to these steps at a later time. So design the vertical curve. Let S be less than L. So L will be AS square divided by 120 plus 3.5 S. So what's A? A is the algebraic difference in grade percentage. Okay, so A equal the absolute difference between G2 minus G1 equal 8 minus 3 equal 5. So the length of the curve will be 5 multiply S, which is 181.4 square divided by 120 plus 3.5 multiply 181.4 equals. So this is 1 square multiply 5 divided by so the length of the curve, it's 217.85 meter. So that's the minimum length of the curve. Again, this is a sag curve. The sag curve, we have 3 design criteria. So we need to check. Okay, first of all, we are not going to use this value. We need to round this value to the nearest 10 to be 220 meters. Why? This way you can adjust the stations and the increment of the stations in a consistent way that does not generate problems. So here we need to do checks. What are the checks we need to make? We need to check on the passenger comfort, the drainage, and the appearance. So here, these are the checks that we need to make. Oops. So we have AV square over 395 يبقى AV square over 395. That's for passenger comfort. So A is 5 multiply 90 square divided by 395. So this will result in 5 multiply 90 square divided by 395, 102.53 meters. So this one is passed. The second one is for the drainage. L over A must be less than or equal 51. So L, here that's drainage, over A equal 220 divided by 5 equal 220 divided by 5, 44, which is less than or equal 50. So here less than or equal 51. So this is okay. What is the last check? The appearance. The appearance, the minimum length L minimum should be 30 multiply A. In appearance, 30A. 30A, that means 30 multiply 5 equal 150 meters. So we passed these. So this way our design is acceptable and reasonable, and there's no problem with it. So what's the next step? We need to determine the stations for the point of vertical curve and the station for the point of vertical tangent. So now we need to go here and let's calculate stations. When we say design vertical curve, that means you do all of this, then calculate the stations. So the station for point of vertical curve equal the station for point of vertical intersection minus L over 2. Okay, so the elevation for point of vertical curvature equals the station, or I'm sorry, the elevation for BVI minus the grade G1 multiply L over 2. So that's BVC, point of vertical curvature. Let's do this. So the station for BVC equal the station of BVI, which is the middle one here. Because here we have two segments. One segment, second segment. So that's the first station. Station 1, 2, 3. 1, 2, 3. So here we have 2 plus 872.0 minus 220 over 2, L over 2 is 110. So the station will be 2 plus 762.0. The elevation for the BVC equal the elevation of that point, which is the point of vertical intersection, 2.88 minus, okay, because we are going this way, we are going in a decreasing order, minus G1, which is 3%, 0.03, multiply L over 2, which is 110, equals 219.58 meters above mean sea level, and this is positive. Okay, there is a very common mistake that I've seen always, that people forget and put here the percentage value, not the fraction value. Okay, because sometimes one of the students, he answered this minus 500 something. Okay, and there is, that's maybe in the ocean. For the point of vertical tangent, the station of BV tangent equal the station of BVI plus L over 2. So here it's going to be 2 plus 872.0 plus 110. So here will be plus 2982.0. The elevation for the point of vertical tangent will equal basically elevation of the point of vertical intersection plus G2 multiply L over 2, because we are going up here. So here will be 222.88 plus 0.08 multiply 110. So this would be 231.68, and here positive, meters above mean sea level. Clear? Please note with me that these stations are not station 1 and this station is not station 3. Clear? Any questions so far? Okay. We're gonna stop here, and next class inshallah we're gonna continue on estimating the equivalent grade. And okay, before we stop, let me ask a question. Do you know determine whether a climbing lane is needed for this segment or not? No, I think we keep it for the next lecture inshallah. Any questions so far?